Okay, so maybe I'll restart a little bit early just because there were a lot of questions. Okay, so let me answer the question explicitly, and then I guess because there's so many questions, let me spend 5 minutes just describing what we did in this proof without any of the bothersome notation. Okay, so for the question was, why do we know that the complement of omega is not connected? So this was the definition that we gave for simply connected, right? So we want to prove that if omega is not simply connected, then there must exist a curve whose Winding number is not 0 for a point outside of omega, right? Because the goal was to prove that this definition of simply connected, of the complement of omega in the extended plane being connected, is equivalent to having that the Winding number of any curve in omega with respect to any point outside of omega is 0, right? So the goal was to prove this equivalence, and so we proved that if the complement is not connected, then we can find a curve whose Winding number is not 0. Okay, so because I'm realizing that maybe this is it's one of those things where the proof really isn't that complicated, but there's like a lot of notation stuff at play. So let me just give a description of what's going on with trying to use as little notation as possible. And then we'll prove Cauchy's. And then turns out the proof of Cauchy's theorem is essentially the same. And so, yeah, and so like this idea is important. Let me go over it again. Yeah, if anything is not clear, please don't hesitate to say, because it helps me a lot knowing what's clear, what's not, just know what to focus on and not. So the goal was to prove the equivalence between the two sort of notions of simply connected, right? So I'll do a 5-10 minute redo of that proof just to with pictures rather than notation, make things a bit more clear, right? So we wanted to show region, right? So this throughout is always a region, right? So open and connected. Okay, so we take a region and we want to say that, in the extended plane, out not counting the region, so the complement connected, right, that is equivalent to the following: for all closed curve omega in the region, right, and A not in the region, that the complement, right, that. And for all A, we have that the Winding number is 0. Okay. And then we had two sides of this, right? One was this one, which was easy, right? And the proof, even though in the beginning I hadn't set it up quite right, the proof is really very, very simple. The proof is just the fact that, right, since the complement of omega is connected, right, then it must be inside one of the regions delimited by gamma, right? So if I think of gamma as being like this, there's one of the regions of gamma, and WC must be inside one of the regions, right? One of regions determined by gamma, and it must be the unbounded one because it contains infinity. It must be in the unbounded one, right? Must be unbounded one. Okay, and so if A is inside C, A is inside the unbounded region, right? Let's call this C not containing, say, gamma and the interior of gamma, right? In a notation that showed up in the homework. And so, and gamma A needs to be 0, and this is basically the proof, right? This was the proof of the easy side. Now for the hard side, I mean hard, it's not really hard, it's just it needs an idea, right? Which is that we start with the complement not connected. And since it's not connected and it's closed, there must exist A and B such that A union B are the complement and A intersected B are nothing, and A and B are closed, right? And now because of this, let's have the picture in mind, right? This is like the set A, this is my set B, maybe I should say this is my part of my set B, right? Let's say, right? There could be other holes, right? Okay, and now this is omega. And so the idea is to create a curve that goes around a point in a way, right? The goal here is to show that this is not true, right? And so what we do is we take a point A here, and now we fill the whole space with little squares, right? Centered around A. And we fill it small enough, right? We keep going and so on, small enough so that no square can touch both A and B at the same time. So they are of small enough radius, right? Of small enough side length, right? And then what we do is we create the curve is just going to be the sum of the boundaries of the curves that bound all of these rectangles, right? And so in the end, you get a curve that looks like this, right? Because of the cancellations, you get a curve that looks like this. Say this touches there. I mean, okay, my picture is hard to, right? But something like this, right? And so you get a curve that doesn't touch A, right? And there's some kind of, curve around A that doesn't touch A. It also doesn't touch B because there is no square that both touches the set A and B. And so the winding number of this curve, right, is exactly the winding, I mean, it's the sum of the winding numbers of each one of the squares, but only one of them contains A inside. So this is 1, and the curve doesn't touch A and doesn't touch B, and so it must be inside omega. And so we found that with this, there must exist a set A in the there must exist a point A in the complement, and there must exist a curve which is contained in omega such that n omega A is equal to 1, right? This was the proof, right? Here explained in 5 minutes, okay? Okay. Is there any other questions that I should, something else I should clarify, or is it all clear? Yeah, okay. If anything is not working right, please let me know. Okay, so I'll erase this and let's go into Cauchy's theorem. Yeah, let's say. Okay, so Cauchy's theorem won't just be true for all curves inside a simply connected region. It will actually be true for all curves that sort of the region. The point being that it's okay if the region is not connected, right? If I have it's not simply connected. Let's say I have a region like this, right? This is omega. If my curve doesn't go around that hole, right? If my curve gamma goes like this, then this should be perfectly fine, right? And that's really the general notion of Cauchy's theorem. And so let me give the definition of homology, right? So this is the idea of homology. A curve will be homologous to 0 if I can sort of continually perturb it to a point right? But I don't want to talk about continuously perturbing curves. And so I'm just going to say that, right, it's homologous to 0 if for every point in the complement of omega, the winding number is 0. Okay, so let's give another definition. Okay, so homology. So a cycle or a closed curve, right? A cycle, gamma inside a region, right? The region omega, right, is homologous to 0, right? And we write that gamma is like 0 modulo this, modulo the region, right? If and only if for all points outside on the complement of the region, we have that NA is 0. Okay? So if a cycle or closed curve, this is the word we've been using more, the term closed curve. Right? We say that it's homologous to 0 if for any point in the complement, the winding number is 0. Right? So here, this curve would not be homologous to 0 because clearly there is a point inside that, right? There is a point here which is in the complement of omega because omega doesn't contain this part for which the winding number would be 0. And in particular, right, we write that gamma is congruent to 0 mod omega, right? Just like in number theory. And we say that, right, we say that gamma 1 is homologous to gamma 2 if and only if gamma 1 minus gamma 2, right? It's clear what I mean by this. I just mean loop around gamma 1 and then around gamma 2 in the opposite direction is congruent to 0 mod omega. Okay. And so now we're ready for Cauchy's theorem in sort of its full generality. Okay. Maybe before I mention Cauchy's theorem, I should say that this is sort of the basis of algebraic topology, right? Because you can imagine that we're now defining, if you think of the set of curves, right, quotient on this, with this quotient that two curves become homologous or become the same in this set, in this quotient space, when their difference is homologous to 0. Right now we can think of the algebraic set of just the curves up to homology, right? And this will have a certain algebraic structure. We'll talk a little bit about it later. And this is exactly what gives rise to algebraic topology, right? It's precisely this algebraic structure, which for simply connected is a very boring algebraic structure, right? Because everything is homologous to 0. But for regions omega that are not simply connected, this becomes a lot more interesting, and maybe I'll talk a little bit about it because that's the basis for something called the calculus of residues. Okay, so Cauchy's theorem, all right, so general Cauchy's theorem. Okay. Right, so a region okay, let's say F omega to C is analytic, then then the integral over some closed curve. Okay, so I should say it's a region. Let me say over some closed curve of FZ dz is equal to 0 for all closed curves for cycles omega, gamma, sorry, such that gamma is 0 mod omega. Okay, so Cauchy's theorem says that the integrals around the integrals on a closed curve on a curve that sum all goes to 0, they are 0. Okay, and so an immediate corollary of this, right? So an immediate corollary, right? So corollary, right? So immediate